Hello and welcome. It's wonderful to have you here as we set out to explore the exciting world of training large neural networks. Today, we'll delve into an intriguing piece of research titled DeMo, Decoupled Momentum Optimization, from the innovative team at Nous Research. Now, you might be wondering, what exactly does that mean? Well, let's imagine teaching a group of eager students in a classroom. When the class gets too big, we split them into smaller groups with different teachers, but we need all the teachers to stay in sync to ensure everyone learns the same material. In the world of artificial intelligence, the students are enormous neural networks with billions, sometimes even trillions of parameters. That is, the knobs and dials that adjust how the network learns. Teaching these massive networks requires multiple teachers or accelerators like GPUs working together. Traditionally, these accelerators need to share information frequently to stay coordinated. They exchange gradients and optimizer states, which are like notes on what they've learned and how they're learning it. This constant communication demands specialized high-speed connections. Imagine needing a super-fast internet connection just to keep everyone on the same page. These connections are expensive and limit where we can train these networks because all the accelerators need to be physically close. Here's where the brilliance of DeMo comes in. The researchers at Nous discovered that we might not need all this chatter between accelerators. They proposed decoupling the momentum updates during training. In simpler terms, they allowed each accelerator to have its own learning speed and direction without constantly checking in with the others. But how do they ensure that everyone still ends up teaching the network effectively? They applied a clever technique from signal processing called the Discrete Cosine Transform, or DCT. Think of DCT like breaking down a complex melody into its fundamental notes. It helps identify which parts of the information are most important. During training, they used DCT to extract the fast-moving components of the momentum, the most critical updates that have the biggest impact on learning. These key components are much smaller in size than the full set of data. By sharing just these essential pieces between accelerators, they greatly reduced the amount of data that needed to be exchanged. In fact, they cut down the communication requirements by several orders of magnitude. That means they reduced it to a tiny fraction of what it used to be. To put their method to the test, the researchers trained large language models, which are neural networks designed to understand and generate human language. They used a model with 1.18 billion parameters, a substantial size, and compared the performance of DeMo to a standard optimizer called AdamW, which is commonly used but requires a lot of communication between accelerators. The results were impressive. Despite significantly reducing the communication overhead, the models trained with DeMo matched or even exceeded the performance of those trained with the traditional method. For example, when training on a dataset of 100 billion tokens, which are the basic units of text, the DeMo-trained model performed just as well on language understanding benchmarks. What does all this mean for the future of artificial intelligence? By reducing the need for high-speed connections, DeMo allows us to train large neural networks using more readily available hardware setups. This could make advanced AI research more accessible and cost-effective, as we're no longer constrained by the need for expensive infrastructure. In summary, the DeMo Optimizer offers a new way to train large neural networks efficiently. By decoupling momentum and sharing only the most crucial information between accelerators, we maintain performance while drastically cutting down on communication needs. It's a practical and innovative solution to a significant challenge in the field. Thank you for joining me on this journey into the cutting-edge techniques of neural network optimization. I hope this discussion has illuminated how smart ideas can lead to big improvements in technology. Until next time, keep pondering and stay curious about the fascinating world of artificial intelligence.